In this video, I want to show you how you run through the analysis on the Whirly Gig Lab, which is the lab that we took the data virtually, and then one group in the class got to use it. I have the full intention of letting the other group use it whenever we get back in school. I don't know when that is. So basically, the lab setup is a hollow tube. There's a string hanging here. We use a clip to basically set the radius of this string. There's a swinging mass. It's a little mass. I usually use a little m for that. And then there's a hanging weight off here, a bunch of washers, right? And I'll use a big M for that. And essentially, what's happening here is you've got two things going on here. You've got the hanging weight. Its downward force of gravity is counteracted by this force of tension. I'm going to use an F sub t here so that we don't confuse it with the period. And then the tension is the same in the string, but the tension here causes centripetal acceleration. So basically, if we drew a second law expression out for that mass right there, we would expect those forces to balance out. The tension is up, the gravity is down, and then when we look at this one, that's what's moving in a circle. So we would say sigma f equals little m v squared over r, where again r is the radius here, and then that would be equal to just the force of tension. So when you look back over here, the force of tension is equal to the hanging weight's force of gravity. So then you can substitute that in, and you get this. And basically, you can kind of see how the hanging weight would affect the velocity. But ultimately, what we had you guys do is measure the period here. So the next thing to do would be to take the expression V equals 2 pi r over the period capital T. Remember, that's not tension. That's the period capital T. And we can substitute that into there. And then what ends up happening is you get M 2 pi r over the period. We're going to square that whole thing, then we're going to divide by r. And then this is mg. So, got our work cut out for us here. M 4 pi squared r squared over t squared, and then we're dividing by r again, and we have mg here. One of those r's cancels out. We're basically going to look to try to kind of isolate the t squared, if you will. So if we multiply both sides by t squared, that'll get us to this point here. And then the last thing to do would just be to divide both sides by capital Mg. And if you did that, you would get that t squared equals, let's write 4 pi squared r lowercase m all over Mg. So this is going to be basically the golden expression, if you will. And essentially, it allows us to relate the period, which we measured, to the radius r, the swinging mass m, and the hanging weight, the washers, capital M. And then this is the key to linearizing your data sets, because all those data sets you took are nonlinear. So when you look at, let's rewrite it out here, this expression, I believe in part 1, what we did was we varied the hanging weights, which were big M, the number of washers. So we varied this right here. So if I just kind of pull this out, let's rewrite this just really quickly as 4 pi squared r m over g, and I'm going to pull out this. This is the key to seeing what we need to plot. Basically, you would want to make this your y data, you would want to make this your x data, and then this would be your slope. And in this experiment, what we did was we set the value of r, we set the value of the swinging mass, lowercase m. If you get the slope of your graph, this is a very fancy way to calculate g. You can calculate g, and if you get anything near 9.81 after you set your slope equal to this expression here, then the experiment worked out nicely. And then we varied other things, right? This was only part 1. In part 2, what we varied was we varied the length of the string r, so that determined, or that gave us different radius. So let's actually pull the r out from that expression, and this is actually probably a little bit easier to do. Take a look here. if you try to plot t versus r, it's nonlinear. But if you plot t squared versus r, then you make that your y data, make that your x data, your slope ends up being this. So you can fit that slope. Now, in this experiment, this and this were held constant. You know what those values are. So again, you can measure g. And if g is, or you could calculate g. And if g is anywhere near 9.81, you've done it properly. And the last one would be, we could pull out little m. All right, so let's write 4 pi squared r over mg. Put the little m over there. There's our x data. There's our y data. So we want to plot t squared versus m. And then this is going to be your slope. Again, you can calculate g from this once you fit your data. And it's a good experiment if it ends up anywhere near 9.81. So ultimately what we did was a fancy experiment that allows us to determine the gravitational constant g.